तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we were discussing about the wastewater treatment and the various processes that are employed for the treating the wastewater. Number one, we said about the primary treatment, and we have seen the various units that are put in place to remove the suspended solids. Second thing, after that we discussed about the secondary treatment, wherein we aim at removing the organic matter, dissolved organic matter. So, today we will discuss about what is called a tertiary treatment, third degree type of treatment to the wastewater to remove certain special components present in the wastewater. So, if you look at the wastewater, it contains several components. For example, the wastewater contains what is called solids. Wastewater contains solids. The solids could be divided into two types. One is the suspended solids, and then is dissolved solids. The suspended solids could be again two different types. One is inorganic suspended solids, inorganic in nature, and another is organic in nature. So, we have got both inorganic and organic suspended solids. Similarly, for dissolved solids also we have got inorganic solids and organic solids. So, these are the, as far as the solids are concerned, these are the things which are present. Now, in the primary treatment, just to recapitulate primary treatment, what we tried to do was try to remove inorganic solids, mainly inorganic solids, and to some extent we also remove organic solids. Extent organic suspended solids are removed. So, that means I am trying to remove the inorganic solids suspended, and also I am trying to remove organic solids suspended in this. So, to some extent inorganic, I think I should say here suspended solids. In the primary treatment, okay, this is the objective. In the secondary treatment, we try to remove the solids again, basically organic in nature, okay, organic dissolved solids are removed in the case of secondary treatment. So, that means as far as the primary and secondary treatments are concerned, we are trying to remove the inorganic solids, to a great extent organic solids. Now, if you see the composition of wastewater, wastewater consists of various components, like I would say that carbohydrates, undigested carbohydrates which we take, and composition of wastewater, and it consists of proteins, undigested proteins, and it consists of lipids. These are the three major components which are coming out in the wastewater. Okay. All these things are organic solids, organic in nature, and they are organic in nature and they are also biodegradable. In other words, I will say biodegradable organic components or compounds. Now, if you take proteins, proteins are special importance actually for the tertiary treatment, which we are going to discuss now. The proteins are contain carbon, hydrogen, oxygen, carbon, hydrogen, oxygen and nitrogen. They contain nitrogen compounds which are of importance. Okay. The nitrogen compound which is important here, okay, this is a nitrogen compound which is important, that is going to be causing some problems. Now, what will happen is this nitrogen which is present in the proteins is in the form of ammonia, that is fresh wastewater, that is not septic. Fresh wastewater contains proteins, undigested proteins. I will put it an adjective here, undigested proteins. These undigested proteins are converted into amino acids. Proteins are converted into amino acids. Protein is a polymer of amino acid, that is this is AA, amino acid, is converted into amino acid by microbial action, and this amino acid is further degraded into by deamination reaction. This amino acid and deamination reaction is removal of ammonia. Deamination reaction, which is mediated by microorganisms, microbes. All these reactions are mediated by microorganisms, converted into ammonia, and this ammonia is present in the wastewater. The ammonia which is present in the wastewater is converted into what is called nitrite and then goes to nitrate. That is, ammonia is oxidized to nitrite and to nitrate. So, this step is known as nitrification, and nitrification is carried out by microorganisms. Okay. So, during this process, this is an oxidation process, and during the oxidation process oxygen is required, and this has oxygen demand. Ammonia exerts oxygen demand for conversion of nitrite and nitrate. So, this is called nitrification. This is again microbial reaction. This is a microbial reaction. There are two types of microorganisms which bring about this reaction. Okay. So, after that, suppose the nitrate is present in the effluent. Okay. Suppose if this oxidation takes place, nitrate is present in the effluent. Nitrate, when it is discharged, nitrate effluents, nitrate containing effluents, nitrate contain effluent, if it is discharged into the water, if discharged, they cause some problems. The problems that are caused are eutrophication of rivers. Eutrophication is nothing but excess growth of algae or prolific growth of algae. Algal growth takes place, excess growth of algae takes place if nitrate is present in the effluent, and that nitrate containing effluent is discharged into the rivers, nitrification will take place. And second thing is that if the water is used for the water supply, if the river water is used as water supply containing high content of nitrate, you know what is going to happen. Methemoglobinemia is the disease which is going to cause to the children, that is called a blue baby syndrome, which we have discussed already. So, the nitrate as such cannot be discharged into the environment. I cannot discharge nitrate containing effluent into the river waters, and for that what I have to do is I have to convert this nitrate into some other compound which does not create a problem. So, what I do is this nitrate is converted into sort of reduced into nitrogen gas. So, this is a reduction, again there is a microbial reduction, and this is called denitrification. Denitrification is a process by which the nitrate in the effluent, this is a effluent, is converted into nitrogen gas which goes to the, this is a gas which goes to the atmosphere. So, what I have done is that ammonia which is present in the wastewater is converted to nitrate, and that nitrate is reduced to nitrogen gas by denitrification process. So, this process is carried out by denitrifying bacteria. Denitrifying bacteria are the ones which cause this reduction. So, finally, I am producing nitrogen gas. So, I have taken care of ammonia and producing the nitrogen gas. Nitrogen gas is not a pollutant, that is what we know. Now, coming back to the slide here, we can see that the tertiary treatment is aimed at removing nutrients, that is nutrients are nitrate and also phosphorus, and make the effluent recyclable. I would like to make the effluent recyclable so that I can use the water. So, then if you see the flow diagram, effluent from the secondary treatment plant comes to what is called nitrification tank, where this nitrification tank, in the nitrification tank what happens? Ammonia is converted to nitrate, and the effluent goes into a denitrification tank. In the denitrification tank, the nitrate that has been produced by the oxidation of ammonia to nitrate is reduced to nitrogen gas. So, in this particular thing we are producing the nitrogen gas in the denitrification tank. After that, the wastewater is allowed, this is a effluent from the secondary is allowed to go to a unit called phosphate removal. The phosphate removal plant could be biological in nature or it could be physical, it could be chemical in nature. So, the biological phosphorus removal is normally employed. After this, after removing the phosphorus also causes excess algal growth. Okay, algal growth is caused by the phosphorus also. So, I am removing the nitrate as nitrogen gas, and phosphate is also removed by the microorganisms. After that, I will pass the water or this particular thing to what is called a carbon adsorption columns. Carbon adsorption columns or granular filtration, and granular filtration or granular filtration. The purpose of doing so is to remove any organics, trace organics that are present. Okay. So, I would like to remove trace organics that are present, and that means I want to make this effluent reusable, recyclable. So, that means either I can use carbon adsorption or ion exchange, okay, or granular filtration. One of the options can be used. After that, we use the chlorination. The effluent is chlorinated either using the conventional chlorine or it could be UV radiation, because chlorine is causing some problems nowadays, and hence we go for the UV radiation. After this particular thing, we have got a recyclable effluent, that can be recycled. We can use it for various other purposes. Recyclable effluent is present here. Okay. This can be used for the water for gardening or flushing or particularly for some other problems. So, this is the tertiary treatment which is very specific which is not mandatory at this moment of time to use the tertiary treatment, but primary treatment and secondary treatment we should have it. Primary treatment and secondary treatment removes number 1 the suspended solids, number 2 the organic matter present in the wastewater, and also we also disinfect it to kill the microorganisms. That is the primary and secondary treatment, while tertiary is optional. So, if you want to reuse the water, you should, if you want to recover the water from the effluent, we can use the tertiary treatment. For that you have to spend money, that is nitrification, denitrification, phosphorus removal, carbon adsorption, and chlorination should be there for this particular thing. So, with this particular thing there are 3 different types of treatment systems. We will look into now more specifically about each one of these systems. Of course, I will be aiming at looking more details of primary treatment and secondary treatment. So, let us go to the primary treatment, more details of primary treatment now. Primary treatment is a physical chemical process. So, I would like to go into the primary treatment of physical chemical unit. So, here this is a physical unit process, and these are aimed at removing inorganic solid mostly and organic solid to some extent from wastewater. In fact, it entails what is called a solid liquid separation process, that is a sedimentation. We use a gravity sedimentation for the solid liquid separation process, and since it is a gravitational process, the physical laws govern the process. So, we can use a physical laws, that is classical mechanics can be used for design of systems to remove the solids from the liquid. So, like sedimentation tank and so on and so forth. Some of the examples of the primary treatment systems are, we have seen in the last class, and elaborating on that, I have got the screens are there. We have got grit removal, grit is removed. Third one is a sedimentation tank with respect to primary treatment of water and wastewater. That means, we have got mainly the screens, then grit removal, grit chamber, and then sedimentation tank. However, what we could do is a physical unit process can also include gas transfer. So, that is a gas transfer is also important physical unit process that we employ for the removal of iron. How do we remove iron? Iron is oxidized, that is ferrous iron is oxidized to ferric iron, and ferric iron is removed as ferric hydroxide. So, this particular thing I have already discussed as an example. For removal of iron, we use the aeration or the gas transfer. Removal of iron, removal of manganese, manganese also should be removed. Manganese also can be removed by the aeration and precipitation and sedimentation, and then we can also use aeration for the taste and odor causing organics. To remove the taste and odor causing organics, we can use gas transfer. Taste and odor causing organics are generally the volatile in nature. Whenever the volatile organics are present in water and wastewater, by supplying the oxygen, by putting the oxygen in it, what we can do is by forcing the oxygen with turbulence into the water wastewater, we can drive out the taste and odor causing organics. And also, we try to saturate the water and wastewater with oxygen, because if oxygen is present in water, it is very pleasant, okay, pleasant feeling we will get it. So, the wastewater also is saturated with oxygen by gas transfer. This oxygen, when it enters into the wastewater, then what does it do? It supplies the oxygen to the microorganisms. The microorganisms utilize the organic matter and then produce carbon dioxide and water. The pollution is removed. So, that is what normally we do with this particular thing. So, next let us take one by one the screenings. The objective of the screenings is to remove floating objects that are present in the wastewater, which if they are not removed, what is going to happen? They clog the pumps, they damage the pumps and valves, pipelines, and other appurtenances that are present in the wastewater collection system. So, the wastewater collection system is hampered, is damaged because of the floating objects that are present in the wastewater. So, the screenings are aimed at removing this particular thing. Next, the floating material like sticks, okay, this and wood, rags is nothing but the cloth that people use, and diapers for babies and so on and so forth. Now, it is a prevalent usage of diapers, napkins, sanitary napkins and other things, and other lightweight objects. All these things are found in the wastewater, and all these things, if they are present in the wastewater, they are going to damage the pumps. They clog the pumps, they damage the pumps, valves and so on and so forth. That is why they need to be removed. Now, some of the design aspects, we have to design the screens. What are the design aspects of the screens? So, there are two types of screens, one is a fine screen and another is a coarse screen. Fine screen is characterized by the opening, the diameter of the opening size is less than 15 mm, that is a fine screen, and the coarse screen has a coarse screen, or it is also called as a bar screen because it is a bigger opening. So, that is greater than 15 millimeters is the opening size of the screen. Then these screens are usually made up of bars, rods or wire grating or wire mesh or perforated plates. These are the materials that are used, and these are various shapes. It could be bars, it could be rods, it could be wire grating and mesh type of thing. And shape of the opening is either circular or rectangular. That means between the two bars, okay, it could be a circular opening or it could be a rectangular opening. That is what we have said. Then once you have this grating, these screens in the direction of flow, the flow passes through this particular thing. I will show you the diagram. The flow passes through these screens and other things, and the material get deposited on the screens. So, that material which gets deposited on the screen should be removed. So, that is done by cleaning. Cleaning can be done by two types of cleaning. One is cleaning can be manual. We can manually clean it, remove the screenings, that is the deposit, you can remove it, or by mechanical cleaning. There are mechanical cleaners also, mechanical cleaning devices are available for this. Then the bar screens, these are bar screens are the coarse screens, all what we discussed is the fine screens. Bar screens are made up of vertical bars. So, there is not much difference between the fine screens and coarse screens in terms of the design, but only thing is that the coarse screens remove a bigger material and the fine screen will remove a finer material. So, that is what it is. So, this is the design aspect of screens. If you say this is a plan view and this is a section, the top one is a section of the screens. So, the wastewater is coming in here, this is the direction of the flow of wastewater, and there is an inclined, okay, the bar screen, the screen is there, and if you see in the plan, this is the screen what we have, this is the screen what we have, and then these screens have got the openings between these two things. You can see the openings, and the materials are sort of deposited, and this particular thing is moving up, and then this is a place where the perforated metal platform for the screenings. Screenings are deposited here, and that screenings are removed manually. Then we have the wastewater going out. So, this is a very simple arrangement of the screens that is possible for removing the floating material from the wastewater. Next, this is another picture of the screens which can be automatically can be operating, and then you can remove the screenings. Now, the third one is some of the design aspects of these screenings are indicated here. This table tells some of the design aspects. For example, type of screening device, what type of screening device we have, and then here size classification, size and classification. Third is the size range in millimeters, and then screen media, what type of media with which it is made, and then applications of the screens and also the figures which I am going to present afterwards. Now, let us see the vertical this type of screening devices. One is inclined. I will like to suggest one thing. So, this is a fixed type of screen. Then you have got a medium size characterization, and it has got a size of 0.25 to 2.5 millimeters is the size of opening of the between the screens, and then this is made up of stainless steel and also stainless steel wedge wire screens. So, the purpose of this is a primary treatment. It can be used for primary treatment, and then the figure I will show it later on. Second thing is a drum. Drum is a rotating type of screen where the flow is there, flow passes through it, and then the material is screened. So, this is normally coarse, and then size is 2.5 to 5 mm. Here you say 0.25 to 2.5 mm is the fine. Here it is 2.5 to 5 mm is the size, and then this is also stainless steel, and the primary treatment, okay, and also primary or preliminary. Some people call it as a preliminary treatment also, and the figure is there. So, we have got the coarse, medium, and then fine type of things, and we have got the mechanical reciprocating type of thing, and another thing is the sort of tangential type of thing. So, we will like to discuss the various types of screens. We can see here in the pictures. So, this is one type of screen which I have indicated 6.3, and this is a drum, okay, rotating drum type of screen, and we have here, this is also again another type of screen for a very big wastewater treatment plant, okay, that is in operation. So, now this is again another type of screen where the material comes in here, the liquid comes in and flows through this and gets screened. So, the effluent after screening will go out like this. This is the direction with which go. This is the influent, and this gets screened and it goes out in this effluent, and the screenings are collected at the bottom. At the bottom the screenings are collected. So, this is another thing where you have got a this is a scraper blade where the screenings are removed from this thing. So, here again another modification of that particular thing. Now, if you look at the design aspect, how do we design these screens? Screens, I am talking about the very simple type of screen. So, the screens are designed based on the approach velocity, okay, and also the channel in which the screen is placed. The channel should be straight forward, okay, the straight section of the channel should be there. About 10 to 15 meters straight channel should be there. So, design approach is minimum velocity is 1 meter per second to avoid settling of solids. This is the biggest problem. The problem is that if you do not maintain a velocity which is sufficient for the particles to remain in suspension, then what would happen to the particles? Particle will settle down in the channel, and once the particles settle down in the channel, the capacity or the carrying capacity of the channel is reduced, and the solids tend to settle down, and then they biodegrade and cause lots of nuisance. That is why a minimum of 1 meter per second velocity should be maintained to avoid settling. The head loss, whenever the flow is taking place through the screens, okay, and when the particles get deposited on the screens, there is going to be pressure drop or head loss. That head loss of head is given is a function of approach velocity, velocity with which the liquid is coming, and velocity through the bars. That means approach velocity, velocity with which the water is coming, wastewater is coming, and also the velocity through the bars, through the screens. So, that is given by HL is equal to V square, capital V square minus small v square over 0.7 into 2g, where HL is head loss in meters, 0.7 is empirical discharge coefficient or value to account for eddies and turbulence losses. V is the velocity through the opening of the bar, meters per second. V is the approach velocity in the upstream channel. This is also in meters per second. You can see very clearly that the approach velocity is smaller than the velocity through the screens. Why? The velocity through the screens will be higher because area of cross section is going to decrease. That is the reason why the velocity will be higher. That means capital V is the velocity through the openings, that is higher value, and small v is the approach velocity of the channel. Now, if you take the fine screens, then the head loss equation is given by 1 by, that is loss of head is given by 2 into 1 by C into 2G multiplied by Q by A whole square. So, this is the equation that is there. So, where C is the coefficient of discharge, typical value is taken as 0.6 and Q is the discharge through the screen, okay. Q is the discharge through the screen and cubic meters per second. A is the effective open area of submerged screen. That means how much area of the screen is submerged in the liquid, in the liquid, that is given by effective open area of submerged screen, that is a square meters. So, initial head loss, if you see here at the bottom, initial head loss is 0.1 meters. That means if the wastewater is flowing through the screens, there is a head loss, that head loss is 0.1 and then permissible head loss is 0.3 meters. Permissible head loss means when the particles get deposited on the screen, the head loss is going to increase. That increased head loss is going to be about permissible head loss is 0.3. Here is a graph which shows a relationship between the opening between the bars, that is opening between the bars, 2 bars, okay, the screens, and also the amount of screenings, that is cubic meters of screenings per million cubic meters of wastewater. If I pass 1 million cubic meters of wastewater, how much of the screenings will be deposited on my screens. So, that is this particular relationship is given by this. This is taken from Metcalfe eddy wastewater treatment. So, this is the maximum value is given by this particular curve. This is a maximum value, maximum amount of screenings, okay. And this gives average value. Average value is this value, average value. What do you mean by maximum value and average value? Maximum value is when the flow is maximum, flow rate is maximum and the average is average flow rate. For average flow rate, what is the cubic meters of screenings that have been deposited on the screens per million cubic meters of wastewater, that is what it gives. And as you see here, as the opening of between the bars is increasing, the opening between bars is increasing, the amount of screening is going to decrease, because why? What is the reason why it is going to decrease? Because some of the material will escape out of the screening, they will be going in the effluent. That is the reason why, see, at 1 centimeter width the screening is removed is so much, and if you have 3 centimeters is a bar spacing, so the screening is very less. So, that is what screening is going to be less if you increase the space between the screens, okay. The next is next important unit operation in the treatment plant, in the physical treatment plant is comminuting. Comminuting means grinding the large objectives that are present in the large objects, not objectives, objects, grinding large objects that are found in the wastewater. Large solids are shredded, that means cut into small pieces, okay. Shredded means cut into small pieces approximately of the size of 8 mm, and these small pieces are allowed to get into the wastewater to remain as solids. So, we would like to allow these these solids to be present in the wastewater, okay. So, these large solids are cut into pieces and then they are allowed to go into the wastewater. So, many of the sinks, that is sinks in the kitchens, have got these grinders at the bottom. The purpose of the grinder is that when you put some of the material, that is the food particles and the residue of vegetables, so on and so forth, bigger than the size, what they will do is that they will grind it, okay. This grinder is placed underneath the sink, okay, in most of the developed countries. So, that will cut into or shred into small pieces, and those material will go into the wastewater. This would eliminate solid waste handling problem. The most important thing is, so from the kitchen waste etc., we can eliminate the solid waste treatment handling problems. A basic part of a screen is in the form of a slotted drum and a cutting tooth. Okay, slotted drum and a cutting tooth is the one which cuts, which shreds the large solids into small particles. Cutting tooth is a stationary cutting, it is a stationary cutting tooth, shred the screened material. The material is screened and then it is shred by the stationary cutting tool. And by having this type of thing, that is a shredder, that is a cutter or cutting teeth, and also a slotted drum which is acting as a screen, we can avoid a separate screens. We can avoid separate screens. We do not have to have separate screens. Commuting itself can do shredding and as well as the screening. Design aspects of the shredders is similar to the screens. So, that is what I do not will go into the details, because it is similar to this particular thing. So, now let us take the third important unit in the primary treatment is a grit or grit chamber. So, grit has to be handled. So, municipal wastewater, if you consider the municipal wastewater, is an assortment, that means it is a combination of various things. Okay, it is assortment of things like inorganic solids. It contains inorganic solids such as pebbles, sand, silt and eggshells, glass, metal fragments. All these things are present in the wastewater, the municipal wastewater. And then they also have organics such as bone chips, seeds, then coffee and tea grounds. All these things are present in the wastewater. So, these are all termed as grit. We term this as grit. Grit is not just sand. Grit is pebble, sand, silt, eggshells, glass, metal fragments. All these things, we have a habit of throwing everything into the sink or everything into the water closet, so that the water closet takes away from our sight the unwanted material. So, organics such as bone chips, seeds, coffee and tea, so on and so forth, these are all called grits. Suppose if the grit is present in the wastewater and if I do not remove it, what is going to happen? So, this grit is abrasive, okay, and cause accelerated wear and tear of pumps and sludge handling equipment. This is very important. It corrodes, it erodes, okay. Sometimes it may not corrode, but it erodes, okay, abrasive and cause wear and tear, accelerated, speeds up the wear and tear of the pumps and sludge handling equipment. So, we have several sludge handling equipments which go out of order because of this wear and tear. Then this grit deposits wherever it is possible. Where it is going to deposit? It is going to deposit most likely in places where low hydraulic shear is there. Low flow conditions are there in pumps, in pipes, sumps and clarifiers. Clarifiers are the sedimentation tanks which we are going to use. All these grits is going to settle down there whenever there is a low hydraulic shear. Low hydraulic shear means when there is not much of the, when we do not have much of what is called the velocity, and they absorb grease. This grit has another property because it offers lot of surface area, and because they offer surface area, the grease and oil and grease which is present in the wastewater gets absorbed onto the grit, okay. So, as a result of which absorbs grease and they solidify, and as a result of which there are what is called a grease balls are produced. We will have a grease balls, so which produce this grit. On grit the grease is adsorbed, and the grit definitely are non-biodegradable. They are non-biodegradable organics. They cannot be degraded because bone chips is non-biodegradable, eggshell is non-biodegradable, grit is non-biodegradable, pebble is non-biodegradable. So, being non-biodegradable they just sit in the sludge digesters, that means in reactors where the reactors which we are designing for the treatment of organic matter, in those reactors they occupy the space, occupy the valuable space in the sludge digesters. They just go and sit there, they cannot be removed, they cannot be degraded, they are conservative chemicals. So, they keep on accumulating as a function of time. Therefore, it is very essential to remove, desirable to separate grit from the organic solids. I have to separate the organic solids from the grit, because organic solids are biodegradable, organic solids undergo a change, they are non-conservative, while the grit is conservative chemical, it cannot change. So, it occupies the space. So, that is why we should remove the grit from the wastewater before it goes to the secondary treatment. So, we have grit removal facilities, many grit removal facilities are there. One of the easiest, one of the most common grit removal facility is have an enlarged channel area, that means a channel is there carrying the wastewater. I suddenly increase the sort of channel area, I increase the channel area, I make this channel width bigger, and thus increasing the channel area is increased. And when I increase the channel area, what would happen to the velocity? Would it remain same? No, it would not remain same, because the channel velocity is there, and as soon as I increase the area, the velocity reduces. When the channel area is increased, the velocity is reduced, and this reduced velocity allows the particles, that is the grit, to settle down by gravity. So, that means it allows gravity settling of the grit will take place. And most recent ones are, this is enlarged area, channel type, that is just whatever we discussed, enlarging the channel area, decreasing the velocity and increasing the, that will sort of enhance the settling of the particles. Second thing is aerated rectangular basins. We have got a rectangular basins specially designed as the grit chambers, and wherein in the rectangular basins again the same principle, I am going to decrease the velocity of flow, and when the velocity of flow is decreased, particles will settle down in the basin, okay, in the chamber, in the grit chamber, and they are also aerated. The purpose of aeration is that I do not want to make the whole sewage septic, that is one thing, I will aerate it, and also this aeration will keep supplying the oxygen for the microorganisms that may be present in the wastewater. So, aerated rectangular basins are generally used in the western countries. However, in India mostly we have got the channel type of grit removal facilities. And then the deposited grit, at the bottom of the tank the grits are deposited, the deposited grits is removed by mechanical scraper. So, that means there is a endless chain moving up and then the grit is removed. So, let us see some of the aspects of grit removal facilities, the various parameters that we can see. Design parameters for the aerated grit chambers. Again I am taking the source from the Metcalfe and Eddy in the book, and we have got these dimensions. Depth is meters, 2 to 5 meters, that is the range, the depth of the grit chamber. The length of the grit chamber is about 7.5 to 20 meters, it could be varying between 7.5 to 20 meters, and the width is varying between 2.5 to 7 meters, and width to depth ratio is 1 to 1.5, okay, 1:1, or these are the values, and the typical is 2:1, 2 to 1 is the that is width is 2 and depth is 1. So, I have the length, so on and so forth, and the detention time at peak flow, that is in minutes, is 2 to 5 minutes. The detention time is the time for which the flow is staying in the aeration grit chamber, the flow is remaining in the grit chamber, that is the time. So, that is at the peak flow, okay, not at the average flow, maximum flow, okay, maximum flow, the minutes 2 to 5 minutes it will remain in the grit chamber, and then the typical value is 3 minutes. So, normally if you want to design a grid chamber, the grid chamber should be designed based on this 3 minutes detention time. Okay, 3 minutes is the detention time. Now, if it is a aerated grid chamber, we need to supply the air. Okay, we need to supply the air. Air is supplied using a compressor. We use a compressor to supply the air. Okay, a blower. So that means cubic meters of air per minute. Okay, per minute meter length of the grid chamber is 0.15 to 0.45. So this is the air that is to be supplied. And next, grit and scum quantities that is coming out of the grid chamber. How much is the like screenings? Okay, the material that is deposited here, also the grit is deposited at the bottom, and that is being removed by endless scraper to the top, and then we have got grit removal is cubic meters per 1000 cubic meters. Cubic meters of grit per 1000 cubic meters of this thing is equal to 0.004 to 0.2. The typical value is 0.015 is the amount of grit that is going to that is collected in this. So now there is one formula which I would like to stress, that is, in order to find out the peak flow. Peak flow is the flow. Okay, peak flow is a flow, or this is a peaking factor. In fact, this is a peaking factor. Peaking factor is given by a formula 5 divided by p to the power of 1/6, and where p is the population in thousands. Population thousands. That means if I know the average flow, then I can find out the peak flow very easily. So that means let us work out an example here at this point of time, so as to show this particular thing, how we use this peak flow, and also use the design parameters we can try to work out. So let me go to this board, and let us work out that particular thing. Now we will try to locate the grid chamber. Grid chamber. So the design considerations or design parameters. One of the important design parameter for this is what is called a surface overflow rate, which we will discuss in the sedimentation tank. Surface overflow rate, or this is also called surface loading rate. Surface loading rate is nothing but the rate at which the surface area of the grid chamber is loaded with the flow. That means this is surface loading rate is nothing but the flow rate over area. That is the flow rate of flow of water discharge, and then this is the area of the surface. So this is nothing but velocity, Vs. So this Vs is a velocity is equal to Q by A. Q is the flow rate and A is the area of the surface of the tank. So that is what it is about, Vs. And now this Vs is nothing but the settling velocity of the particle. Settling velocity of the particle. Of a particle, of a design particle, of a critical, I will put it here, critical particle. Okay. So the Vs is given by Stokes law, G by 18 nu Ss minus 1 into dp square. This is the settling velocity Vs is the settling velocity, where Vs is the settling velocity and g is acceleration due to gravity, and nu is the kinematic viscosity of water, kinematic viscosity of water, Ss is the specific gravity of the particle, Ss is the specific gravity of the particle, and dP is the diameter of critical particle, that is what is diameter of critical particle. Suppose if I want to remove a particle with a diameter dP of 0.1 millimeters, 0.1 millimeters is a grit diameter of the grit is, and then Ss is equal to 2.65, specific gravity is 2.65, and then nu kinematic viscosity is 1.01 into 10 to the power of minus 6 meter square per second. Kinematic viscosity of water is this. Then I can calculate Vs, compute Vs, Vs can be computed, okay, Vs can be computed, Vs is nothing but the settling velocity. Once I compute the Vs, then next what I will do is I will try to find out using this equation. Vs is known, that is computed now, and then Q by A, yes, I will put it, surface area. So the Q is the flow rate. Suppose if I say the Q is equal to 1 million liters per day, 1 MLD, which is equal to 1 MLD means 1000 10 to the power of 6 liters per day. So that is equal to 10 to the power of 3 cubic meters per day, 10 to the power of 3 cubic meters per day. Q is this much, then Q is known, then Vs is known, that you can calculate As. We can calculate As. As can be calculated. As is the surface area. Surface area is nothing but, if you take the plan, that is a plan area. This is nothing but plan area. So surface area, once I get the surface area multiplied by volume of the grid chamber, is nothing but surface area of the grid chamber As multiplied by the depth. So the depth is given to us, so I can calculate the volume of the surface, volume of the grid chamber, that is nothing but V. Once I find out the volume of the grid chamber, then what I can do, I can find out the detention time. Detention time is equal to, that is theta equals V by Q. V is the volume, Q is the flow rate, theta is the detention time. Detention time can be calculated. So all these things are done for a Q, and Q is the average flow. Q is the average flow. The flow is always, I mean, for average flow I can calculate it. Then once I calculate the detention time and also the volume of tank for the average flow, what I need to do is that I have to find out whether this particular system is going to work for peak flow, because you know very well that the flow is not always average. The flow can be less than average, flow can be more than average. So, if the flow is less than average, I do not have to worry. If the flow is more than average, I need to worry. So, for that matter, I need to find out whether my grid chamber is going to work or not at peak flows. So, whether system works at the peak flow or not, I have to find out. So, in order to find out the peak flow, what we have is a peaking factor. Peaking factor is given by the equation P over that is 5 over p to the power of 1/6. This is 5 over p to the power of 1/6, and p is the population in thousands. For example, if the population is 10,000, p will become 10. So, 10 I have to substitute here and take the raised to the power of 1/6 and this particular thing 5 over this one and find out the peaking factor. Now, the peak flow is nothing but average flow Q average, this is a Q average multiplied by peaking factor, peak factor. So, this is peak factor PF. So, I can calculate the peak factors like that. So, peak flow can be calculated. Now, what I have to do is that I have designed a system for the average flow, then I should check whether it is going to work for the peak flow or not. That is, peak flow is always more than the average flow, and then I check it, and if it works, it is fine, the design is fine. That is what we are going to do it.